Microturbines. Microturbines are relatively small combustion turbines that can use gaseous or liquid fuels. While large gas turbines have been used for CHP applications for several decades, microturbines emerged as a CHP option in the 1990s. Individual microturbines range in size from 30 to 330 kilowatts, kW, and can be integrated to provide modular packages with capacities exceeding 1000 kilowatts. Working figure shows an illustration of a microturbine. The heart of the microturbine is the compressor turbine package, or turbocompressor, which is commonly mounted on a single shaft along with the electric generator. The shaft, rotating at upwards of 60,000 revolutions per minute, is supported on either air bearings or conventional lubricated bearings. The single moving part of the one-shaft design has the potential for reducing maintenance needs and enhancing overall reliability. The microturbine produces electrical power either via a high-speed generator turning on the single turbocompressor shaft or through a speed reduction gearbox driving a conventional 3,600 revolutions per minute generator. The high-speed generator single-shaft design employs a permanent magnet and an air-cooled generator producing variable voltage and high-frequency AC power. This high-frequency AC output, about 1,600 Hz for a 30 kilowatts machine, is converted to constant 60 Hz power output in a power conditioning unit. The recuperator is a heat exchanger that uses the hot turbine exhaust gas, typically around 1,200 degrees Fahrenheit, to preheat the compressed air, typically around 300 degrees Fahrenheit, going into the combustor, thereby reducing the fuel needed to heat the compressed air to the required turbine inlet temperature. In CHP operation, microturbines offer an additional heat exchanger package, integrated with the basic system, that extracts much of the remaining energy in the turbine exhaust, which exits the recuperator at about 500 to 600 degrees Fahrenheit. Other than the size difference, microturbines differ from larger combustion turbines in that they typically have lower compression ratios and operate at lower combustion temperatures. In order to increase efficiency, microturbines recover a portion of the exhaust heat in a heat exchanger called a recuperator. The recuperator increases the energy of the gases entering the expansion turbine, thereby boosting efficiency. Microturbines operate at relatively high rotational speeds, often reaching 60,000 revolutions per minute.
Microturbines are used in distributed generation applications. Due to their flexibility in connection methods, their ability to be stacked in parallel to serve larger loads, their ability to provide stable and reliable power, and their low emissions compared to other technologies, microturbines are well suited to be used in CHP applications because the exhaust heat can either be recovered in a heat recovery boiler, or the hot exhaust gases can be used directly. There are over 360 sites in the United States that currently use microturbines for CHP. These microturbine sites represent over 8% of the total number of CHP sites in the United States, accounting for 92 megawatts of aggregate capacity. 2 sites that use microturbines for CHP include hotels, nursing homes, health clubs, commercial buildings, food processing plants, and small manufacturing operations. In CHP applications, thermal energy from microturbine exhaust is recovered to produce either hot water or low-pressure steam. The temperature of microturbine exhaust also allows for its effective use with absorption cooling equipment that is driven either by low-pressure steam or by the exhaust heat directly. Microturbine systems that provide both cooling and heating can be used in a variety of commercial and institutional applications. Microturbines can burn a variety of fuels, making them useful for resource recovery applications, including landfill gas, digester gas, oil and gas field pumping, and coal mine methane use.